Welcome back to Sleepy Orbits. Maybe the house has finally settled into that deep, late-night quiet where the refrigerator sounds like company. Maybe you're tired in the bones, but the mind hasn't gotten the message yet. Either way, you're in the right place. And tonight, I want to open with a piece of paper. A single page of equations written in Berlin in the winter of 1917 by the most famous scientist who ever lived. On that page, Albert Einstein added one small term to the equations of general relativity, a term he did not want, a term he privately admitted disfigured the beauty of his theory. A fudge factor inserted for one purpose only: to stop the universe from moving. 12 years later, the universe was caught moving anyway, and Einstein crossed the term out. He spent the rest of his life regretting it. Legend says he called it the biggest blunder of his career. And here's the thing most people don't realize: that crossed-out term came back. 68 years after Einstein erased it, two teams of astronomers measuring the light of dying stars halfway across the universe discovered something so strange that the only piece of mathematics in all of physics that could describe it was Einstein's discarded fudge factor, lifted from the wastebasket, dusted off and put back into the equations exactly where he had written it in 1917. Today, that term describes roughly 68% of everything that exists, not 68% of the atoms or the stars or the galaxies. 68% of the entire contents of reality, an invisible something that fills every cubic inch of space, pushes the galaxies apart, grows stronger as the universe grows larger, and holds the final fate of everything, every star, every world, every future, in its grip. We call it dark energy, and we do not know what it is. It outweighs in energy every star, planet, galaxy, gas cloud, and unseen halo in the cosmos combined, twice over. But its symbol on every blackboard in every physics department on Earth is still the same Greek letter Einstein wrote and disowned: lambda. The greatest mistake of the greatest scientific mind in history turned out to be, by accident, through no intention of his own, one of the deepest truths about the universe. Tonight is the story of that term: why it was born, why it was killed, how it rose again, what it is doing to the cosmos while you sleep, and the newest twist still unfolding in the observatories this very year, which suggests the story has one more turn left that nobody, not even Einstein, saw coming. One thing before we begin: if you fall asleep partway through, good. That's the point. In the morning, tell me in the comments the last thing you remember hearing. And if you make it to the end, tell me which part of Einstein's beautiful mistake stayed with you and what you'd like us to explore next. If these nights help you rest, a like or a subscribe helps this channel more than you'd realize. Now, let's begin. To understand why Einstein reached for his fudge factor, you have to stand where he stood in 1917, and it is difficult now, more than a century later, to remember how small the known universe was that winter. There was one galaxy, ours. The Milky Way was not a galaxy among billions. It was, as far as the science of the day could establish, the entirety of the material universe. An island of stars a few tens of thousands of light years across, floating in a void that was assumed to go on forever and contain nothing further. The spiral smudges in the telescopes, the objects we now know to be galaxies beyond counting, were widely thought to be little whirlpools of gas inside our own star system, minor local scenery. The universe of 1917 was one city of stars, and it appeared, on every measurement anyone had made, to be sitting still. The stars wandered, slowly, individually, this way and that, but the grand structure showed no signs of going anywhere. Eternal and static. That was not Einstein's prejudice alone. It was essentially everyone's, a background assumption so deep that it had never really been questioned, inherited from Aristotle and Newton and every night sky any human had ever stood beneath. The stars are the very emblem of permanence. It is what we mean when we call something fixed. And it is worth picturing the room where our story starts, because the circumstances make the achievement stranger. Berlin, in the winter of 1917, was a city in its fourth year of war, hungry under the British blockade, its windows dark, its bread adulterated, its casualty lists lengthening. Einstein himself was unwell that year, worn down by overwork and wartime rations, nursed through stomach ailments in a cold apartment. A pacifist marooned in the capital of a war he despised. And in those conditions, between illness and ersatz coffee, the man sat down with the equations he had finished 2 years earlier and asked them the largest question ever posed by a member of our species. What is the shape and story of the universe? All of it, as a whole. While the guns spoke in France, a sick man in a hungry city was quietly founding cosmology. Whatever else tonight's story says about his stumbles begin here with the audacity. It had simply never occurred to anyone before that the entire universe was something you could write an equation about and check. And Einstein had just finished building the most beautiful theory in the history of physics, and the theory refused to agree. General relativity, completed in 1915, is a theory of gravity, and we've leaned on it together many times on this channel. So tonight, I'll give you only the heart of it, the one sentence that matters. Matter tells space how to curve, and curved space tells matter how to move. Gravity, in Einstein's hands, stopped being a force reaching mysteriously across distance and became geometry, the shape of space and time themselves, dented and guided by everything they contain. It is the most successful description of gravity ever written. It has passed every test a century could invent, from the orbit of Mercury to the ripples of colliding black holes. And in 1917, Einstein did the boldest thing you can do with an equation of gravity. He applied it to everything. Not to a planet, not to a star, to the universe entire, all matter, all space, as a single system. With that one act, he invented modern cosmology, the mathematical study of the whole cosmos, and he immediately ran into a problem that must have felt like a splinter in the mind. The equations would not sit still, and in fairness to Einstein, the problem he hit was older than he was. It had been quietly embarrassing physics for 2 centuries. Isaac Newton himself, pressed in his letters about what his gravity implied for the heavens, had conceded the difficulty. A finite cloud of stars should all fall together into one great mass, and even an infinite one balances only like a needle standing on its point. Perfect. Until the smallest disturbance, and then collapse. Gravity only pulls. A universe of pure attraction has no way to hold still, and Newton, having no better answer, suggested divine maintenance kept the stars apart. The problem then politely hibernated for 200 years because no one had equations grand enough to force the issue. Einstein's were. When he filled his theoretical universe with matter evenly spread and asked the mathematics what happens next, the mathematics answered, as it had whispered to Newton, motion. A universe full of matter attracts itself. Every galaxy pulls on every other. The whole assembly wants to draw together, and a universe set down at rest immediately begins to collapse. Everything falling toward everything, slowly at first, then faster. His equations offered him a universe like a ball thrown in the air, permitted to be rising, permitted to be falling, forbidden to hang motionless. And hanging motionless was, as far as all of astronomy could tell, exactly what the real universe was doing. The theory demanded drama. The sky showed none. Faced with that conflict, Einstein did something that scientists have debated ever since. Something completely understandable and completely fateful. He trusted the sky over the equations. The observations said static. So static, the theory must be made. Understand how small the change was physically on the page, because the smallness is part of the legend. The field equations of general relativity, the complete law of gravity for the whole universe, are compact enough to print on a coffee mug, and physicists do. What Einstein added on the left-hand side was one term, the Greek letter lambda, multiplying the geometry of space. A single character. In the entire history of writing, no other single character has carried remotely so much. Added in 1917, deleted in 1931, restored in 1998, and today holding 2/3 of the known universe in its account, still just one letter long. He found the theory could accommodate exactly this one kind of modification, a single extra term the mathematics happened to permit, consistent with all the theory's principles, which he had left out originally for the simple reason that nothing required it. He called it the cosmological term and wrote it with the Greek letter lambda. And what lambda did, physically, was strange and new. It endowed empty space itself, the pure vacuum, with a faint built-in tendency to push apart. Not a force between objects, but a gentle outward pressure belonging to space as such, everywhere, always growing more significant across larger distances. Tuned with exquisite care, this built-in push could exactly balance the inward pull of all the universe's matter, and the cosmic ball could hover, a universe held forever motionless between gravity and lambda, like an arch standing on the perfectly matched opposition of its stones. That was Einstein's universe of 1917, finite, serene, eternal, balanced on the edge of a knife. He never loved it. That deserves saying clearly tonight, because it is the detail that makes everything that follows so human. Einstein's genius was aesthetic as much as anything. He trusted beauty in equations the way sailors trust weather, and lambda, he knew perfectly well, was ugly. It answered no principle. It emerged from no deep necessity. It existed to make the answer come out the way the astronomers said it should, and Einstein said as much in print, writing that the term was gravely detrimental to the formal beauty of the theory, and admitting the constant was justified only by the goal of making the equations match a quiet sky. He had spent a decade following beauty to the deepest truth about gravity anyone had ever found, and then, at the final step, at the scale of the whole cosmos, he flinched. He patched his masterpiece to agree with the astronomy of the moment. It is the most relatable thing the man ever did. Every one of us has, at some hour of some night, altered a good idea to please the room. Einstein just happened to do it in the equations of the universe, and the room happened to be wrong, because the sky was lying, or rather, the sky was whispering, and the instruments of 1917 could not yet hear it. The universe was not static, it was moving, magnificently, in a way nobody had imagined, and the evidence was already beginning to pile up in an observatory in Arizona in the patient spectrograms of Vesto Slipher, who had been measuring the light of those little spiral smudges and finding to his growing bafflement that nearly all of them were rushing away. And the first crack in the static universe appeared within months from inside Einstein's own circle. The Dutch astronomer Willem de Sitter, one of the first people in the world to master general relativity, took Einstein's new equations, lambda and all, and found a second universe hiding in them, a universe containing almost no matter at all, ruled by lambda alone. And de Sitter's empty universe did something scandalous. It expanded. With no matter to hold it, lambda's push ran unopposed, and any two test particles set down in that cosmos would flee each other at ever-increasing speed. Einstein disliked the solution intensely and spent years trying to rule it out, but there it stood, legal and irrefutable. His own anti-gravity term, invented to enforce stillness, was capable, in the right universe, of powering runaway expansion. Hold that thought all night, because it is the entire ending of this story, visible in the first year, in the mathematics, unrecognized. The de Sitter universe of 1917 is, near enough, a portrait of where our real universe is now heading. The prophecy was on the table before the 20s began. Everyone mistook it for a curiosity. The room, meanwhile, was about to change its mind about stillness altogether. And the first people to say so out loud, the first to read Einstein's own equations with a straight face and report what they actually said, were two men outside the inner circle. A Russian mathematician who taught himself relativity between wars, and a Belgian priest with a taste for the beginning of the world. Neither owned a telescope, neither needed one. Between them, armed with nothing but Einstein's own equations taken at their word, they found the real universe on paper years before anyone saw it in glass. Alexander Friedmann was a meteorologist and mathematician in St. Petersburg, a man who had flown balloon ascents to record-breaking altitudes and taught bombing crews ballistics in the First World War. And when the war ended, he taught himself general relativity from the papers as they arrived in Russia. In 1922, working through Einstein's equations with fresh eyes, he did the simple, radical thing. He declined to assume the universe stand still. He let the equations speak, and out of them poured a family of universes nobody had ordered, universes that expand from a dense beginning, universes that expand, slow, halt, and collapse, universes that expand forever. Whole cosmic biographies, birth to death, sitting inside Einstein's own mathematics, waiting for someone willing to read them. Friedmann published, respectfully noting that the static case was just one special member of a much larger family, and mailed his work into the world. Einstein's response has become one of the cautionary legends of science. He wrote a public note declaring Friedmann's results suspicious, claiming to have found an error that invalidated the whole business. He had not. The error, when the dust settled, was Einstein's own, a slip in his checking, and to his credit, he published a retraction admitting Friedmann's mathematics was correct after all. But even then, even in the draft of his own retraction, he could not resist adding that the expanding solutions were mathematics only, that a physical significance could hardly be ascribed to them. Think about that sentence tonight. The equations were his. The solutions were correct, and he admitted it, and still he waved them away because they described a universe in motion, and everyone simply knew, the universe sat still. Friedmann never got to see the verdict. He died of typhoid in 1925 at 37. Having glimpsed the expanding universe in pure mathematics years before any telescope confirmed it, and having been told by the greatest physicist alive that his universes were dreams. Then came the priest, Georges Lemaitre, whom we've met before on this channel, veteran of the trenches, ordained Catholic priest, and one of the finest cosmologists of the century, rediscovered the expanding solutions independently in 1927, and he did something Friedmann had not. He connected them to the sky. Lemaitre knew about Slipher's fleeing spirals. He put the equations and the observations side by side and said the unsayable plainly. The galaxies are not flying through space away from us. Space itself is expanding, carrying them apart, exactly as relativity permits. He even derived the law, the proportionality between a galaxy's distance and its apparent speed of retreat, 2 years before the man whose name that law would carry. And when Lemaitre buttonholed Einstein at a physics conference in Brussels that autumn to press his case, Einstein delivered the review that Lemaitre would remember and quote for the rest of his life. "Your calculations are correct," Einstein told him, "but your physics is abominable." There it is again, the same reflex. The mathematics unimpeachable, the universe unacceptable. Twice now, the equations of general relativity had tried to tell their own author that the cosmos was dynamic, once through a Russian and once through a Belgian, and twice the author had told the messengers, in effect, that their arithmetic was fine and their reality was in poor taste. What broke the stalemate was not argument. It was a mountain in California, a 100-inch mirror, and the man we've already followed through another night's story, Edwin Hubble. Through the 20s, Hubble first proved that the spiral smudges were entire galaxies far beyond the Milky Way, inflating the known universe a millionfold in one stroke. And then, in 1929, combining his galaxy distances with those redshift measurements, he published the pattern that ended the debate. The farther away a galaxy lies, the faster it recedes. Double the distance, double the speed. It was the fingerprint Friedman's mathematics had predicted and Lemaitre had described. The signature not of galaxies fleeing through space, but of space itself stretching everywhere at once. The telltale, then and now, is a property of light itself, worth 30 gentle seconds at this hour. Light is a wave, and its wavelength sets its color, with blue at the short end and red at the long. When light crosses expanding space, the space it is traveling through stretches beneath it in transit, and the wave stretches with it, sliding the light toward the red. Astronomers call it redshift, and it is the odometer of the cosmos. The longer and farther the journey, the more expansion the light has endured, and the redder it arrives. Every galaxy, Slipher and Hubble measured, wore its distance in its color, and the rate they uncovered, refined by a century of measurement, is worth translating once tonight, because it reveals how whisper-gentle this mighty process is at any human scale. Space the width of our entire Milky Way galaxy, 100,000 light-years of it, grows by roughly the length of a small town, a couple of kilometers each second. Across your bedroom, the corresponding stretch is billionths of a trillionth of the width of an atom, utterly erased by the room's own bindings. The universe expands the way a glacier flows, invisibly at every instant, irresistibly across the ages. And before we go on, let me retire the question that visits everyone who meets this idea at 1 in the morning. Expanding into what? The honest, settled, strangely soothing answer is into nothing, because it does not need anywhere to go. The expansion is not the universe swelling outward into some waiting emptiness like a balloon in a room. There is no room, no outside, no edge being pushed forward, and no center where it all began. The Big Bang did not happen at a point out there. It happened everywhere, including exactly where your bed is now. And the expansion since has simply been every distance within the universe growing all at once, with no one anywhere privileged. Every galaxy sees the same retreat of all the others. Every observer everywhere appears to be the center, which is the surest sign that no one is. Nothing needs to exist beyond the universe for the universe to make more room within itself. The loaf does not rise into the oven, so to speak, it simply rises. If that refuses to picture neatly in your mind tonight, be comforted. It pictures in no one's. The mathematics carries what imagination cannot, and it carries it perfectly. Some truths we hold with equations, the way we hold hot things with tongs. The static universe, the eternal backdrop, the assumption beneath 10,000 years of stargazing, was simply wrong. Everything is in motion. The whole sky is leaning apart. Einstein, to his lasting credit, did not go to his grave defending the fudge. In the winter of 1931, he traveled to California, by then the most famous face on Earth, mobbed at every station, and made his pilgrimage up the winding road to Mount Wilson itself, where he met Hubble, examined the 100-inch telescope, and looked with his own eyes at the data. The visit produced one of astronomy's most beloved, possibly embroidered, anecdotes, as the observatory staff proudly explained that the mighty telescope existed to determine the structure of the universe. Einstein's wife Elsa is said to have replied that her husband did that on the back of an old envelope. The story may be too good to be true, which is its own kind of truth about how the world saw the man. But what mattered happened in the data room. The envelope this time yielded to the telescope, and he yielded completely and publicly. Within months, he published a new model of the cosmos, expanding, dynamic, built on Friedman's despised solutions, and from it he deleted lambda entirely. The constant was, he wrote, no longer necessary. The expansion itself resolved the problem lambda had been invented to solve. The term vanished from his equations and nearly from respectable physics. And here the legend attaches, the one carried into the world decades later by the physicist George Gamow, who wrote that Einstein had told him in conversation that the cosmological constant was the biggest blunder of his life. Historians, I should tell you honestly, have never found those words in Einstein's own hand, and some doubt he ever put it quite that way. The phrase may be Gamow's polish on a milder German regret, but whatever the exact words, the substance is not in doubt. Einstein regretted lambda. He regretted the flinch, the patch, the trust placed in a quiet sky over his own beautiful equations. If he had held his nerve in 1917, if he had believed the theory instead of the astronomers, he could have stood before the world and announced that the universe itself must be expanding or contracting a decade before any telescope could check, and been proven right on the grandest possible stage. Physicists still speak of it wistfully as the greatest prediction never made. Relativity had already performed its miracle once, bending starlight by exactly the foretold angle in 1919 and making Einstein the most famous scientist alive. Imagine the sequel, the same man reading the birth and motion of the whole cosmos out of pure mathematics before the evidence existed. It was sitting in his own handwriting, complete, spoiled by one added term. He carried that for the rest of his life. He died in 1955, believing lambda had been a scar on his masterpiece, an error redeemed only by erasure. He never softened on the point either. If there is no quasi-static world, he wrote, then away with the cosmological term. For Einstein, the matter was closed. The term had been an answer to a question the universe turned out not to be asking, and honesty demanded its deletion. But not everyone agreed, and tonight, knowing the ending, the dissenters read like prophets. The great British astrophysicist Arthur Eddington refused to give lambda up, arguing that a constant woven so naturally into the equations would not be there for nothing. And Lemaitre, the abominable priest, went furthest of all. He kept lambda in his cosmology for the rest of his life, and in 1934 he published a sentence that reads today like a message sent 7 decades ahead of schedule. The cosmological constant, Lemaitre proposed, should be understood as the energy density of the vacuum itself, empty space possessing a weight and a pressure of its own. That is, almost word for word, the modern definition of dark energy. The priest had not only midwifed the expanding universe, he had correctly identified in the 1930s what the 21st century would find running it. Almost no one paid attention. The idea sat in the literature like a seed under snow, waiting 64 years for its spring. Einstein was wrong about lambda's death then, and the proof would take 43 more years, a revolution in telescopes, and the deaths of a very large number of distant stars. To feel the size of what happened in 1998, you need the question the 20th century spent its second half asking. Once you accept that the universe is expanding, one great question rises above every other, and it is really a question about endings. Does it stop? The expansion began in the Big Bang, the hot, dense birth we visited on other nights, and the story of how that birth was confirmed deserves its 2 minutes here, because it decided whose universe we live in, and because it delivered one of the kindest moments in the history of science. Through the 50s, the expanding universe still had rival interpretations, and the decisive test was a prediction. If the cosmos began hot, the heat should still be here, cooled by expansion into a faint glow of microwaves arriving evenly from every direction, the embers of the beginning. In 1965, 2 radio engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were wrestling with a stubborn problem in a horn-shaped antenna built for satellite work. A faint, steady hiss they could not eliminate, the same in every direction, day and night, season after season. They checked the wiring. They pointed away from New York. They famously evicted a pair of pigeons roosting in the horn and scrubbed away what their paper delicately called a white dielectric material. The hiss remained. Meanwhile, 40 miles away at Princeton, a team of physicists was building an antenna to search for the predicted glow of the Big Bang. And when the two groups finally compared notes, the Princeton leader put down the phone and told his colleagues, "Boys, we've been scooped." The annoying hiss was the afterglow of creation. Penzias and Wilson had discovered the baby picture of the universe by accident while trying to make a phone antenna behave, and it earned them the Nobel Prize. The expanding, evolving universe was no longer an interpretation. It had a photograph. And in the summer of 1966, in a hospital in Louvain, word of the discovery was brought to the dying Georges Lemaitre. The abominable universe was confirmed. The priest, who had been scolded by Einstein, lived just long enough to learn that the beginning he proposed had left a light, and that the light had been found. The expansion has been carrying the galaxies apart ever since, with the afterglow cooling quietly behind it. But all those galaxies pull on one another. Gravity never sleeps, never takes a century off, and every pull between every pair of galaxies works against the expansion, a brake applied to the whole cosmos. So the story seemed to reduce, beautifully, to a single contest. The outward coasting inherited from the beginning versus the inward break of all the matter there is. A ball thrown upward from the surface of the earth. Throw it gently, and gravity wins. It slows, stops, and falls back. Throw it hard enough, and it escapes, slowing forever, but never stopping. The universe, it seemed, must be one throw or the other, and each throw is a destiny. If gravity wins, the expansion someday halts and reverses, and the universe falls back into itself over billions of years, galaxies drawing together, skies brightening, everything returning to density and fire in a final collapse. The big crunch, a big bang run backward, possibly some speculated, the seed of a next bounce. We wondered that possibility together on the night about the universe before this one. If gravity loses, the expansion coasts outward forever, thinning and cooling without end, stars burning out generation by generation into a long, cold twilight. Fire or ice. Those were the menu's two items, and the deciding factor was simply weight. Count up everything the universe contains and you would know how hard the brake is pressing, and therefore how the story ends. It became one of the great projects of 20th century astronomy. Weigh the universe, learn the future. Cosmologists spoke of the critical density, the knife-edge weight that separates the two fates, and expedition after expedition of measurement came back with the same maddening result. Count everything: stars, gas, even the dark matter by its gravity, and the universe held barely a third of the critical weight. Yet other evidence kept insisting the total books must balance at exactly the critical line. A third of the ledger accounted for, 2/3 of reality simply missing. Through the mid-90s, a few theorists pointed out, in papers read politely and shelved, that there was one old piece of mathematics that could supply the missing entry, smooth and invisible and everywhere. But reviving the blunder term of 1917 on bookkeeping grounds struck most of the field as an accountant's desperation. The missing two-thirds stayed missing, an open wound in the inventory, as if the answer was straining towards some third option nobody was willing to write down. One thing everyone agreed on, though, one certainty shared by every camp. Whatever the answer, the expansion must be slowing down. That was not a hypothesis. It was barely even considered a question. Gravity attracts. Matter fills the universe. Therefore, the expansion decelerates, and the only issue worth funding was by how much. Hold on to how reasonable that certainty was, how bedrock, how obvious. Every physicist alive would have signed it. The measurements of the 1990s were designed explicitly to measure the amount of the slowing. Nobody was looking for what they found. The tool of the search you already know from another night, from inside the dying stars, the exploding white dwarfs, the Type 1a supernovae, the thieving dwarfs that detonate at the same critical mass everywhere in the universe, and so blaze with nearly the same true brightness every time. Standard candles measure how bright one appears from Earth, and you know how far its light has traveled. Measure the stretch of its light, and you know how much the universe has expanded during the journey. Each one is a lamppost with the date of its light's departure written on it. Find enough of them, near and far, and you can reconstruct the expansion's whole history, decade by cosmic decade, and watch the breaking happen. The catch was ferocity of effort. Such supernovae are rare, a couple per galaxy per millennium, visible in their brightness for only weeks. To catch them by the dozen, astronomers had to photograph thousands of galaxies, again and again, subtracting image from image, chasing every new spark with the world's largest telescopes before it faded, night after night, year after year. By the mid-1990s, 2 teams had taken up the hunt, and the story is better because there were 2, because they were rivals, and because they could check each other. One was the Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, a physicist who had spent nearly a decade inventing the search techniques, the software, the scheduling tricks that turned supernova hunting from luck into harvest. The other was the High Z Supernova Search Team, an alliance of astronomers led by the young Brian Schmidt in Australia, with Adam Rees doing much of the crucial analysis, hardened observers who knew every way a supernova could fool you. The 2 teams raced across the same sky for the same prize, sharing little, checking everything, each keen to be first to announce the number everyone awaited, the deceleration of the universe. Through 1997, the data accumulated, supernova by supernova, each one a dot on a plot of distance against expansion, and slowly, in both war rooms independently, the dots began to drift to the wrong side of the line. The distant supernovae were coming out too faint, fainter than they should be at their redshifts, as if their light had traveled farther than any decelerating universe would allow, as if the expansion, since their light departed billions of years ago, had not been slowing at all. The teams did what good scientists do with an impossible result. They attacked it, themselves mostly. Perhaps intergalactic dust was dimming the distant explosions they tested, and dust could not do it. Perhaps ancient supernovae were intrinsically dimmer. They tested. The explosions looked the same in every era. Perhaps some subtle bias in the search, in the calibrations, in the software, months of hunting turned up nothing. Ries ran his final analysis and found the effect glaring back at him out of his own arithmetic, and famously described the team's reaction as somewhere between amazement and horror. Schmidt said his own first reaction was that surely they had made a mistake. Perlmutter's team, staring at the same drift in their own independent data, went through the same stages. And in early 1998, first one team and then the other went public with a number nobody had asked for, and it was not a deceleration. The expansion of the universe is speeding up. Sit with the wrongness of that for a moment, the way the physicists of 1998 had to. The universe is full of matter, and matter attracts. An expansion that speeds up is a thrown ball that climbs faster the higher it rises, a stone that leaps from your hand and accelerates into the sky. It offends the deepest instinct in all of physics, the instinct that says gravity gathers, gravity slows, gravity reels things home. For the expansion to accelerate, something must be pushing. Not pushing from somewhere like an explosion at a center, but pushing everywhere, evenly, gently, a pressure resident in every parcel of the cosmos, strengthening its grip on the whole as the whole grows larger. Some influence woven into space itself, with the strange property that more space means more push. You have heard that description before. You heard it near the start of tonight. An outward tendency belonging to empty space as such, everywhere, always, more significant across larger distances. It is lambda. It is exactly, precisely lambda, the fudge factor of 1917, the term Einstein invented to hold the universe still, deleted in 1931, regretted until his death in 1955. When the supernova teams and the world's theorists went looking for mathematics to describe the acceleration, they did not have to invent anything. The mathematics had been sitting in the literature for 80 years, complete, consistent, wearing Einstein's own handwriting. The term went back into the equations in the exact spot it had been erased from. Nothing about it needed changing but the value. Instead of tuning lambda to freeze the universe, nature had apparently tuned it smaller, small enough to lose the early tug-of-war against matter, but patient enough, as we'll see, to win the late one. Einstein's mistake was not the term. His mistake was the reason for the term, and the erasing of it, and, above all, the modesty of his imagination about what it might mean. He had discovered the right ingredient for the wrong purpose, at the wrong strength, for a universe that does not exist, and then thrown it away. and the real universe had been quietly running on it the entire time. The community, it must be said, did not swallow the result instantly. A claim that sighs from data that hard-won earns its skepticism. But this is why it mattered that there were two teams, rivals, using independent data, independent software, independent chains of reasoning, arriving at the same impossible answer in the same season. Each team was the other's confirmation, and in the years that followed, the acceleration was checked by entirely different kinds of cosmic measurement. The afterglow of the Big Bang, the clustering of galaxies, the bending of light by cosmic structure, and every independent road led to the same place. The journal Science named the discovery breakthrough of the year for 1998, and then came the years of stress testing, because extraordinary results earn extraordinary auditing. Theorists proposed every alternative dignity could permit. Perhaps gravity itself misbehaves across billions of light years and needs modification. Perhaps we inhabit an unusual region, a great local hollow, whose emptiness mimics acceleration. Perhaps some exotic dust, some evolution in the supernovae, some crack in the ladder of distances. Each alternative was worked out honestly and tested hard, and one by one they strained and failed against the widening data. The decisive third witness arrived in the early 2000s when a satellite called WMAP mapped the Big Bang's afterglow in exquisite detail and delivered an independent audit of the universe's entire energy budget. No supernova involved. Its books balanced only one way: a flat universe whose dominant component, about 70%, was smooth, gravitationally repulsive, and invisible. The same answer from the universe's oldest light that the dying stars had given from its recent history. When two completely different messengers born 13 billion years apart agree on the same strange number, the number stops being a claim and becomes an era. Cosmologists call what followed the age of precision cosmology, and its constitution is the lambda CDM model. 13 years after the announcement, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe, one half to Perlmutter, the other half jointly to Schmidt and Rees, the two rival war rooms honored as one discovery, which, in the end, is exactly what their rivalry had guaranteed it was. The something doing the pushing needed a name for the popular conversation, and the cosmologist Michael Turner supplied one that stuck, coining dark energy as a deliberate echo of dark matter. Two darknesses rhymed on purpose, so that even the vocabulary would remind everyone that the universe's ledger is dominated by entries we cannot see. The name is admittedly a label on an empty box, and physicists say so cheerfully. Naming it was not explaining it. But every mystery needs a handle to be carried by. But on the blackboards, in the equations, it kept the name it was born with in Berlin in 1917, lambda. The standard model of the entire cosmos today, the framework every measurement is compared against, is called lambda CDM. And the lambda at the front is Einstein's, restored, promoted from fudge to foundation, from blunder to bedrock, the first letter in cosmology's description of everything. So what is it? What is dark energy actually? Here I owe you the two honest sentences that frame everything else. First, we can measure what it does with exquisite and improving precision. Second, we do not know what it is. Tonight's story ends at a genuine frontier, one of the 2 or 3 deepest open questions in all of science. And I would not dream of pretending otherwise, but what it does, and what that means for everything you can see from your window, and for the ending of the whole story of matter, that we can walk through together, gently. And it is one of the strangest inventories in nature. Start with the budget of reality, because this is where dark energy's rank becomes almost unbelievable. Add up everything the universe is made of, weighed by its energy, and the atoms, all of them. Every star and planet and person and cloud of gas in every galaxy, everything made of the matter you and I are made of, come to about 5%. A 20th of reality is everything we ever meant by the word everything. Every photograph every telescope has ever taken, from the craters of the moon to the deepest galaxy fields, is a portrait of the minority. The other 95% has never once appeared in an image, only in its consequences. Another 27% or so is the dark matter, a different mystery entirely, and worth keeping distinct in your drowsy mind. Dark matter pulls. It is unseen mass gathered in and around the galaxies, holding them together with extra gravity, and its great prophet was an astronomer named Vera Rubin, who in the 1970s measured the spin of galaxies and found their outer stars orbiting far too fast, whirling at speeds the visible matter could never hold together, unless each galaxy sat inside a vast halo of something unseen. She was doubted, then vindicated, then celebrated. And tonight her name is on the mountain in Chile, on the observatory whose 10-year survey, begun just weeks ago as I speak, will hunt both of the great darknesses at once. The pulling kind she found and the pushing kind this night is about. Dark matter is the universe's hidden glue, and the remaining share, roughly 68%, over 2/3 of everything that exists, is the pusher. Dark energy spread with perfect smoothness through every region of space, indifferent to galaxies, indifferent to structure, the same in the emptiest void as in the densest cluster, patiently levering the universe apart. Glue and lever, pull and push, and between them, our 5%. The atoms, the exception, the trace ingredient, the rounding error that happens to include everyone who has ever wondered about the rest. Now, the property that makes dark energy behave so unlike anything else, the key that unlocks the whole night, its density never thins. Everything else dilutes. Scatter a box of matter through an expanding space and the matter spreads out. Double the volume, halve the density. Light dilutes even faster, stretching and weakening as space grows. That is why the young universe was matter's kingdom. Everything was close together, densities were enormous, gravity ruled every scale, and the expansion slowed, exactly as instinct demands, for billions of years. That deceleration really happened. The supernova record shows it. But dark energy, if it is truly Einstein's lambda, is a property of space itself, and so it does the one thing nothing else can do. As space expands, making more of itself, it makes more dark energy in exact proportion. Every new cubic mile of universe arrives with its allotment included. The density of the push never drops, so the contest between matter and lambda was never a fair fight. It was a waiting game with only one possible winner. Matter's team thins forever. Lambda's team holds steady while the arena itself grows. For the first several billion years, matter was concentrated enough to dominate, and the universe slowed. But expansion diluted matter century by century, eon by eon, until somewhere around 5 or 6 billion years ago, right around the era our own sun was forming, the lines crossed. The push overtook the pull. The breaking universe became an accelerating one, and it has been gathering speed ever since. That is the event the supernova hunters caught in the light of their dying stars. The changing of the guard, the handover of the cosmos, written across the sky in lamps that exploded on both sides of the transition. The handover is permanent, and it compounds. This is the arithmetic that decides everything later tonight, so let it settle in softly. More space means more dark energy. More dark energy means faster expansion. Faster expansion means more space, sooner. The universe has entered a feedback, gentle beyond perception on any human scale, inexorable on cosmic ones, the same mathematics as compound interest or a rumor spreading, or anything that feeds its own growth. Cosmologists can already see where it tends, an expansion that doubles and doubles again on a fixed rhythm forever. And if some ancient part of you flinched at that, if exponential growth in the fabric of everything sounds less like housekeeping and more like destiny, your instincts are good. That is precisely what it is. When we come to the future in a little while, this compounding is the whole plot. And here the universe discloses one of its strangest symmetries, one we brushed against on the night about the speed of light. This has happened before. In the very first instant of time, in the burst cosmologists call inflation, the infant universe underwent exactly this kind of exponential, space-making, runaway expansion, driven by something lambda-like that saturated the newborn vacuum, doubling the cosmos again and again in a sliver of a second before decaying away and handing its energy over to matter and light. The Big Bang's opening act, in other words, was a brief, ferocious reign of dark energy's ancestor. And now, 14 billion years later, after the long Middle Ages of matter, a faint residue of the same kind of influence has outlasted everything and is settling in to rule the endless future. The universe began accelerating and will end accelerating. The era of stars and galaxies and readers and listeners is the pause between two reigns of the vacuum, the calm interval when matter briefly had the upper hand. Some theorists suspect the two reigns are related, that today's dark energy is a distant echo or leftover of inflation's engine. No one knows. But as bedtime symmetries go, it is hard to better. The universe, like any good story, seems to be rhyming its ending with its beginning. But before the future, I owe you the present. And the present holds one of the funniest, most humbling episodes in modern physics. What happened when the theorists tried to calculate lambda from first principles? Because here is the thing. Physics already had a candidate for dark energy ready-made before anyone asked. Quantum theory, tested to more decimal places than any theory in history, insists that empty space is not empty. The vacuum seethes. We met this on the night of the dying stars in the Casimir effect, in the trembling fields between the metal plates. At the smallest scales, space is a froth of fields and fluctuations, energy flickering in and out of existence everywhere, always. Empty space has an energy of its own, and energy belonging to space itself, spread evenly, undiluting, pushing outward, is exactly the job description of the cosmological constant. The identification is so natural it feels inevitable. Dark energy is simply the weight of the vacuum, the hum of the quantum fields at rest. Einstein's lambda explained at last by the other great theory of the 20th century. One small chore remained. Calculate the vacuum's energy from quantum theory and check that it matches the lambda the astronomers measure. The calculation has been done many ways with many refinements, and it produces one of the most famous wrong answers in the history of human thought. The predicted vacuum energy comes out too large, not by a factor of a few, not by a factor of a million. Depending on how the accounting is done, the prediction overshoots the measurement by up to 120 orders of magnitude, a 1 followed by 120 zeros. There is no comparison I can offer that truly holds that number, but let me gesture at it. The ratio of the entire observable universe to a single atom is a factor of about 10 followed by 30-some zeros, and our error is that ratio cubed and then sum. Physicists call it, with the gallows cheer of people who have stared at it for decades, the vacuum catastrophe, or simply the worst theoretical prediction in the history of physics. If the vacuum really weighed what the naive quantum accounting says, the push would be so violent that no two particles could ever have found each other. No atoms, no stars, no galaxies, no you, just instantaneous dilution, forever. The actual lambda, the one running our sky, is unimaginably gentler. So gentle it took nature 9 billion years to promote it to power. So gentle we only noticed it in the 1990s. Somehow, out of the quantum froth's colossal energies, virtually everything cancels, contribution against contribution, positive against negative, to 1 part in 10 to the 120. And what survives the cancellation, the faint residue, the last unpaired whisper of the vacuum, appears to be the thing steering the cosmos. Why the cancellation is so nearly perfect, and why it is not exactly perfect, nobody knows. That double question, so small yet not zero, may be the deepest why in physical science tonight. Some theorists seek a hidden symmetry that enforces the cancellation. Some suspect lambda takes different values in different regions of a vaster reality, and we find ourselves, unavoidably, in one of the rare pockets mild enough to permit astronomers. Some believe the whole framing is wrong, and a deeper theory of space and time will dissolve the question. And wrapped inside the catastrophe is a second riddle, quieter and stranger, called the coincidence problem. Matter dilutes. Dark energy holds steady. Their balance shifts eternally in one direction. For billions of years, matter utterly dominated, and for the endless future, dark energy will. The two are comparable, nearly 50-50 as cosmic bookkeeping goes, for only one relatively brief era in the entire history of the universe. And we live in it. The handover era, the one moment the two great powers stand nearly matched, happens to be the moment observers exist to notice. Coincidence? Perhaps entirely. Someone has to live some time. But it has bothered enough great minds to fuel a famous speculation, and one genuinely eerie success. In 1987, more than a decade before dark energy was discovered, the physicist Steven Weinberg reasoned as follows. Suppose lambda takes many different values across some vaster ensemble of universes. In almost all of them, it is large, and space blows apart before galaxies can form, and no one is home. Observers can only ever find themselves in the rare pockets where lambda is accidentally tiny. And tiny it must be. Ruthlessly, run the models with a lambda even modestly stronger than ours, 10 times, 100 times, still absurdly weaker than the quantum accounting suggests. And the acceleration begins too early before gravity has finished its slow work of gathering gas into galaxies, and the raw material of stars is levered apart before any star can form. A universe of thin, cooling, structureless mist. No galaxies, no suns, no worlds, no winter nights, no listeners. Our existence, Weinberg observed, is itself a measurement of lambda, and a demanding one. But there is no reason for the value to be exactly zero, so observers like us should expect to find a small, non-zero lambda, just large enough to be on the verge of noticing. 11 years later, the supernova teams measured exactly that. Small, non-zero, on the verge of noticing. Whether Weinberg's reasoning explains the value or merely gestures at it is furiously debated, because its price is high. It works only if our universe is one draw from an unimaginable deck. But it stands as one of the few predictions anyone made about dark energy before the fact, and it landed. Meanwhile, for those who'd rather not buy the deck, theorists built the main rival picture. Perhaps dark energy is not the vacuum at all, but a field, a dynamic, invisible, ocean-filling space with its own slow history, able to strengthen and fade across the eons. They named it quintessence, after the fifth element of the old philosophers, the substance the ancients imagined filling the heavens. Keep that word in reserve. It returns at the end of tonight's story wearing new evidence. A century after a term was added to an equation in Berlin, the finest minds alive cannot tell you what it is. They can only tell you, now with beautiful precision, what it is doing. So let's look at that. Let's watch dark energy work. The first thing to understand about dark energy's work is where it does not work, because the moment people hear that space itself is expanding faster and faster, a reasonable dread creeps in. Is it expanding here? In this room? In me? Rest easy on this one completely. No. The expansion of the universe, accelerating or not, operates only where expansion has already won. In the vast open country between the great structures, anywhere gravity has gathered matter and bound it in a galaxy, a solar system, a planet, a sleeping body, the binding winds utterly and locally forever. Your atoms are held by electromagnetic forces trillions of times stronger than any cosmic push across those distances. The Earth is bound to the sun to the Milky Way, and the Milky Way itself is gravitationally lashed to its neighbors, and within all such bound systems, space does not expand, not slowly, not at all, and our harbor is generous. The local group, the gravitational family that no expansion will ever dissolve, holds the Milky Way, the great Andromeda galaxy, the lovely spiral of Triangulum, and dozens of smaller companion galaxies, a fleet several million light-years across, tens of billions of stars beyond our own, all permanently ours. When tonight's story speaks of everything leaving, remember the size of what stays. More worlds than could be visited in 1 billion lifetimes, bound to us forever. Dark energy takes the strangers. The family remains. The dark energy present in the room with you tonight, and it is present, its faint allotment filling the space between you and the ceiling, is overwhelmed there beyond any measurement. Think of the cosmic expansion as a tide that can only lift what no harbor holds. Everything you love is in harbor. The tide works only on the open sea out in the gulfs between the galaxy groups where nothing is anchored to anything, and out there it is the mightiest thing in existence. Let's go there once, you and I, since no one ever does. Settle deeper into the pillow and drift out with me, out of the harbor entirely, past the far rim of the Milky Way, past the last globular clusters hanging like harbor lights, past our little fleet of satellite galaxies, out until even Andromeda is just a bright, lens-shaped smudge behind you, and onward still millions of light years into the true open water between the galaxy groups. Here, there is almost perfectly nothing. This is the emptiest kind of place the universe contains, a handful of atoms per room-sized volume. No stars, no dust, no sound, no up. The nearest anything is farther away than your mind can hold, and the galaxies, all of them, are reduced to what they always really were. Faint, scattered islands of light, embedded in a black so deep and wide it has no shore. Hang here a while. You feel nothing, of course. There is nothing to feel. But this quiet water is where the whole story of tonight is happening. All around you, at every point, silently, without disturbance, new space is arriving. The gulf you float in is growing, gently, on every side, the islands easing apart, not moving, being moved, the black between them accruing like interest in the universe's oldest account. If you fixed your gaze on one far galaxy and waited eras, eons, you would watch it redden, dim, and slide with infinite slowness toward the horizon of the visible, one of the thousands leaving every year. Nothing out here will ever stop it. There are no harbors to be had in the open sea, no anchor to throw, nothing to tie the islands together. This is most of the universe, this widening quiet, and it is dark energy's entire kingdom. No drama, no violence, nothing you could photograph, only distance itself, being manufactured everywhere, forever. And before you turn for home, run time forward just once, the way only imagination can. Watch from this open water as the eons blur past, the islands of light drifting apart slowly at first. Then, as the compounding takes hold with gathering speed, the sky around you thinning, museum halls going dark one wing at a time, until after enough ages, the black holds only your own home group, one glow in an otherwise perfect night, and the open water you float in has grown wider than the whole universe you were born into. That is the tide's full work, complete. It will take 100 billion years of patience to accomplish, and it begins with the gentleness around you now, the quiet arithmetic of a little more room everywhere, forever. Now come back. Ride the long way home to the harbor, into the bound and stable light of our own galaxy, where space holds still and the floor holds up, and your bed sits anchored to a world that cannot drift. Both places are the universe. You get to sleep in the kind that keeps you, and we can watch it working. That is the part that still astonishes me at this hour. The push shows itself in the growing emptiness of the great voids, those continent of nothing regions between the galaxy filaments, swelling measurably as dark energy inflates them. It shows itself in a subtle warming and cooling of the Big Bang's afterglow, as its light crosses growing cosmic structures, a fingerprint called forth exactly when the acceleration began. It shows itself in the slow starvation of the galaxy clusters, structure formation, the gathering of matter into ever grander assemblies that occupied the universe's first 9 billion years, has been losing momentum ever since the handover, the growth of the great filaments and superclusters gently switching off as the raw material is levered out of reach. The universe, if you like, has finished its major construction. The grand webs and walls of galaxies we map tonight are close to the final architecture. Dark energy has quietly announced that nothing much larger will ever be assembled again. The age of building is ending. The age of separating has begun. Here is the strangest, loveliest way to feel the acceleration's meaning, and it needs only one small addition to what you learned on the night we spent at the edge of the observable universe. You may remember the horizon out there, the distance beyond which expanding space carries galaxies away faster than their light can ever close the gap, the border past which events happen that we will never, in any future, see. In a decelerating universe, that border would be a temporary embarrassment. Expansion slowing forever means light eventually wins every race, and patience alone would someday deliver the whole universe to our telescopes. Acceleration reverses the story. In an accelerating universe, the border is not fading. It is closing in the sense that matters. Galaxy after galaxy, the great catalogue of the sky is being carried across the line out of causal reach, each one mailing us its last light as it goes. We spent a whole night with that idea, the night about most of the universe being already gone, so tonight I'll add only the detail that belongs to this story. Dark energy is the reason. Einstein's lambda is the hand closing the door. The accelerating expansion is, right now, removing perhaps thousands of galaxies per year from the volume of the universe that our descendants, with any technology, however magical, could ever visit or signal. Every year, the eventually reachable universe is smaller than it was the year before. You will not feel it. The sky will look identical your whole life, your children's lives, for millions of lifetimes. But the ledger is real, and it only moves one way. We live in a universe that is, at the grandest scale, gently and permanently letting things go, which brings us unavoidably to the question every version of this story must face, the question the 1990s thought they were answering when they stumbled on the acceleration instead. How does it end? What does a universe run by lambda do with its endless future? We've toured cosmic endings together before on the night of the universe's most terrifying ending, and I promised you then that the far future is gentle in its pacing however it goes. Tonight, we can do something more precise. We can follow Einstein's term specifically to each of its possible conclusions, because it turns out the fate of everything depends on a single question about dark energy that observatories are fighting to answer at this very moment. Is it truly constant? Is lambda actually lambda, fixed forever, the same yesterday, today, and in 1 trillion years? Or does it change? Everything, and I mean everything, hangs on that one word: Take the constant case first, the textbook case, the one where Einstein's term is exactly what he wrote, a fixed property of space, eternal and unchanging. This is the standard forecast, the future written in lambda CDM, and it unfolds with the stately pacing this channel loves. So let it play out like the long, slow film it is. For the next few billion years, almost nothing changes that you could see. The Milky Way and Andromeda, bound to each other in their local harbor, complete the merger we watch together on another night. The sun ages and swells on schedule. The acceleration continues, imperceptible in any sky. The first visible consequence arrives across the next tens and hundreds of billions of years, and it is the one you already know. Departure. Galaxy by galaxy, the universe beyond our local harbor crosses the horizon and takes its leave, their light stretching, reddening, slowing to a stop, like a film winding down, each one fading from every telescope, not with a bang, but with a long, red-shifted whisper. The great clusters go, then the nearer groups, until, some 100+ billion years along, the merged remnant of our local group, one grand elderly galaxy of long-lived stars, floats alone in a darkness that was once crowded with millions of visible neighbors. Astronomers who evolve in that era, and the slow red stars will still be warming worlds then, will survey a perfect blackness beyond their own stars and conclude, from all available evidence, that their galaxy is the entire universe, an island in an infinite void. They will be wrong, and they will have no way, even in principle, to discover it. The expansion, the Big Bang's afterglow, the other galaxies, every clue to the true story will have been carried out of reach by lambda. Stay a moment with the tenderness of that. We live in the brief, privileged era when the universe's autobiography is still readable. We can see the beginning's glow and the neighbor's light, and we happen to arrive while both were still on display. Cosmology itself has an expiration date, and we made it in time. If you want to make the forecast personal, you can sort tonight's own sky into the leaving and the staying, and I promise the exercise lands gently. Every individual star you have ever seen with your bare eyes, every constellation, every point of light in every night of your life stays. All of them are our galaxy's own, harbored forever. The Big Dipper is not going anywhere, ever, in any scenario. Andromeda, the one great spiral visible to the naked eye, stays, and more than stays. It is family, bound to us, destined to merge with us. Its stars will someday be our stars. The Magellanic clouds of the southern sky stay. What leaves is everything you need a telescope to love. The Virgo cluster, with its thousands of galaxies, the great Coma swarm, every deep field smudge in every Hubble photograph, the whole magnificent crowd beyond our little group, all of it bound not to us but to the tide. The sky of the deep future, in other words, looks almost exactly like the sky of tonight. The naked eye will never miss what lambda takes. Only the telescopes will inherit the loneliness. It is the strangest mercy in cosmology. The universe is leaving, and the view from your window is staying. And after the isolation, the long quiet that we walked once before, and tonight need only honor briefly. The stars burn down across spans that embarrass the word trillion. The thriftiest red dwarfs alone will glow for something like 10 trillion years, 700 times the current age of the universe. So, the island galaxy keeps its hearths lit for what amounts, from here to practical eternity. But the gas does run dry. Star formation gutters out. The last newborn suns are followed by no others, and the galaxy dims from white to red to infrared to black. Matter itself overstretches for which even scientific notation grows breathless, surrenders to entropy's patient accounting, stellar remnants evaporating their order away, the last black holes sighing out their substance over spans written as a 1 with 100 zeros behind it. And the universe settles toward its final state, a thin, cold, dark, ever-expanding stillness that physicists call heat death, where nothing happens anymore, ever. Not because anything went wrong, but because everything finally finished. If the word frightens you at this hour, remember the consolation we found before. This is not destruction. Nothing tears, nothing burns, nothing is taken. It is the universe completing every process it contains at a pace so slow that calling the numbers astronomical insults them, an ending less like a fire and infinitely more like the deepest sleep, arriving over spans of time you could not exhaust with all the counting in the world. That is Lambda's promised future, eternal, gentle, dark, and calm. As cosmic endings go, and we have shopped the alternatives together, it is, honestly, one of the kindest on offer. To place ourselves in that immensity, borrow the old device of compressing the universe's whole history so far into a single calendar year. The Big Bang rings in the first instant of January the 1st. Our galaxy assembles in the late winter, and the handover, the day dark energy overtook matter, and the acceleration began, falls somewhere in August. A late summer coup, quiet, unnoticed by anyone, because no one, anywhere, may have understood it was happening. The Sun and Earth form in early September. All of recorded human history, every name you know, occupies the final 10 seconds of December the 31st. And the futures we have been describing, the departures, the dimmings, the long quiet, lie not in the next calendar year, but thousands of calendar years further on, each of them as long as everything that has ever happened. We are not creatures of the ending. We are creatures of the first year's summer, wondering on our 10 seconds of New Year's Eve at how gracefully the story is arranged to outlast us. But that forecast assumed the word constant, and physics has learned expensively to double-check the word constant. So consider the second possibility, the one with the memorable name Suppose dark energy is not fixed. Suppose it strengthens with time, its density growing as the universe expands. A possibility theorists call phantom energy. Then the gentle tide becomes something else entirely, because a strengthening push eventually breaches the harbors. Run that mathematics forward and you get the scenario called the Big Rip, and its calculated schedule in one worked example where phantom energy is assumed runs like a countdown reading itself in reverse. Galaxies unbound from their clusters billions of years from now. Then, some 60 million years before the end, our galaxy itself pried apart, its stars released into the dark. The planet stripped from the sun in the final months. The Earth, in this hypothetical, unbound in the last half hour. Atoms themselves torn open in the final fraction of a second as the expansion's strength surges toward infinity and space, in the mathematics at least, ends. I give you the Big Rip tonight, the way one shares a ghost story around a fire. For the shiver, not the forecast. Every measurement we have, and they improve yearly, finds dark energy consistent with gentleness, hugging the constant line or, if anything, leaning the other way, toward weakening, not strengthening. The rip requires dark energy to be a very specific kind of strange for which there is no positive evidence at all. But it earns its place in tonight's story for one reason. It demonstrates the stakes of that single word constant. The difference between the calmest ending in cosmology and the most violent one imaginable comes down to the fine behavior of Einstein's one little term, which is why, in the 2020s, cosmology has bent its whole strength to measuring that term's behavior with new precision. And here, in the last act of tonight's story, the universe has produced its freshest surprise, one still warm from the observatories, one that would have made Einstein sit down slowly in his chair. On a mountaintop in Arizona, on the same peak where Vesto Slipher once gathered the first fleeing spirals a century ago, there is a telescope fitted with one of the strangest instruments ever built, a focal plane carrying 5,000 small robots, each one gripping a strand of fiber optic cable, each able to swivel and point its fiber at a single galaxy. It is called DESI, the Dark Energy Spectroscopic Instrument, and its method is cheerful brute force. Every 20 minutes or so, all 5,000 robots pivot in unison to a new choreography. 5,000 galaxies pour their light down 5,000 fibers at once, and the machine reads 5,000 distances in a single gulp. Night after night, since 2021, it has swallowed the sky in these gulps, 5,000 fibers trembling into new positions in the dome's red half-light, a mechanical meadow turning its stalks toward whatever field of galaxies rises next, while somewhere below, the night's harvest streams away to the computing centers, thousands of cosmic distances an hour, in perfect silence. And this very spring, in 2026, it completed its 5-year grand survey, the largest map of the universe ever constructed. The measured positions of more than 47 million galaxies and quasars, a 3-dimensional atlas reaching back 11 billion years. There is a fine tradition on this channel of pointing at the night subject from your own yard, and tonight's has an address too. On spring evenings, the constellation Virgo climbs the sky, and behind its scattered stars lies the great Virgo cluster, the nearest of the crowds that dark energy will someday escort over the horizon. Find Virgo some clear night, and you are looking directly at the tide line at the near edge of everything that is leaving. It will still be there, I should add, for your great-grandchildren's great-grandchildren, multiplied by a number with more digits than this sentence. The tide is patient, and the pointing is safe. Ruled into that atlas, like a watermark in paper, is an ancient regularity, and its origin is lovely enough to earn its minute at this hour. The infant universe before atoms formed was a glowing plasma in which light and matter were locked together, and through that plasma ran sound waves, actual pressure waves, wrung by the tiny irregularities of the beginning, spreading outward like circular ripples on a pond for 400,000 years. Then the universe cooled, atoms formed, light broke free, and the ripples simply froze mid-spread, their pattern locked into the distribution of matter at the exact radius they had reached. Galaxies later grew where the matter lay, and so faintly, statistically, galaxies to this day prefer to sit at that one special separation from each other. The fossilized wavelength of the universe's first sound, stretched ever larger as space expands, a standard ruler printed on the cosmos itself. Measure the apparent size of that ruler at every depth of the map, at every age of the universe, and you read the expansion's full history with a precision the supernova hunters of the 90s could only have dreamed about. DESI was built, as its name declares, to interrogate dark energy, to take Einstein's term and ask it, era by era, are you constant? Cosmologists compress that question into a single number, and since the whole last act turns on it, let me hand it to you gently. The number is called W, and it describes dark energy's character, how its pressure relates to its density, which decides how it behaves as space expands. If dark energy is truly Einstein's lambda, a changeless property of the vacuum, then U equals exactly -1, tonight, yesterday, and forever, with no possible variation. That single value is the signature of a true constant. Every departure means something alive. A W drifting with time is a field, a dynamic ocean, a quintessence with a history, and more to the point, a future that the constant does not have. For a quarter century, every measurement kept landing on -1 within its errors, and the constant looked serene. The purpose of DESI's 47 million galaxies was to measure U across cosmic history so finely that serenity and disguise could finally be told apart. DESI arrived, it should be said, at a moment when the reigning model had already developed one famous crack, and you deserve the honest context. Lambda CDM is a triumph. Combining the Big Bang's afterglow, the galaxy maps, and the supernovae, it pins the universe's age at 13.8 billion years and predicts a dozen independent observations with uncanny agreement. But for the past decade, two of its finest measurements have refused to reconcile. The universe's present expansion rate, calculated from the afterglow of the beginning, comes out measurably slower than the same rate measured directly from nearby stars and supernovae, and the disagreement, called the Hubble tension, has survived every audit of both sides. It is a story deserving its own night, and it may yet get one. Tonight, it matters as atmosphere. Cosmology entered the 2020s with its standard model strained, listening hard for any further sign that lambda, the constant at the model's heart, is not behaving. Into that listening room, DZ began to speak, and the answer coming back so far is perhaps not constant at all. And the collaboration, nearly 1,000 scientists analyzed its map under a discipline worth admiring: blinded analysis. The pipeline built and frozen while the crucial answer stayed deliberately hidden from its own authors, so that no thumb, hopeful or fearful, could rest on the scale. Only when the methods were locked did they unblind and look. When the DSI team released its first year's analysis in 2024, combining its ruler with the supernovae and the Big Bang's afterglow, the data showed a preference, mild but persistent, for a dark energy that changes, and changes in a particular direction, stronger in the deep past, weakening now. The next year's release, with triple the data, did not dissolve the hint, as statistical flukes usually do. It strengthened the preference, climbing toward the significance thresholds physicists take seriously, though still short, I must say honestly, of the gold standard that constitutes discovery. The supernova evidence itself has been re-fought within this past year, and the episode deserves telling because it shows the machinery of science running exactly as designed. In 2025, a prominent reanalysis argued that subtleties in the supernova data had been mishandled, and that the case for acceleration, the Nobel result itself, was weaker than advertised. Headlines briefly wondered whether dark energy existed at all. The original discoverers, now senior statesmen of the field, went back into the data rooms themselves, audited the challenge as ruthlessly as their own work had once been audited, and this summer published their answer. The challenging study contained identifiable errors, and with those corrected, the acceleration stands as firmly as ever. The pillar held. But notice what kind of decade this has become. The fine print of dark energy, its exact strength, its constancy, its future, is genuinely contested territory tonight, being argued by the best people alive with the best data ever taken in real time. Understand what is being suggested tentatively in those data releases. That dark energy is not lambda, not a constant of nature, but a dynamic thing, a field with a history, something that rose, held the stage, and has now begun, very slightly, to ebb. The evidence remains provisional, and it may yet evaporate. Hints at this level have died before, and every cosmologist would tell you to hold the champagne. The reinforcements, conveniently, are already in the field. Europe's Euclid Space Telescope, launched in 2023, is imaging billions of galaxies across a third of the sky, reading dark energy's history in the subtle shear it leaves on their shapes. The Rubin Observatory, whose 10-year movie of the southern sky began this very summer, will multiply the supernova catalogue of the 1990s thousands of times over, turning the sample that discovered acceleration into a rounding error of its own dataset. And a NASA space telescope named for Nancy Grace Roman, chief of the astronomers, waits in the wings to do the same from orbit. Within a handful of years, dark energy will be measured 3 independent ways at precision the discoverers could not have fantasized about. So, if the hint holds, if those instruments confirm the drift, then the story of Einstein's term acquires a final twist worthy of everything that came before. Lambda, the constant that was born wrong, deleted wrongly, and resurrected in triumph, would turn out to be wrong once more, in a subtler way, an approximation of something alive underneath. Einstein's mistake would have been accidentally right, and then, at the highest magnification, instructively wrong again, pointing past itself at physics nobody has written yet, and the future would reopen. That is the quiet enormity buried in the Diaz-I hints, the reason the announcements rippled far beyond cosmology. Every forecast we walked tonight assumed the constant. A weakening dark energy softens the exile. The horizon's door closes more slowly, or less completely. Weaken it enough in some models, and the acceleration eventually retires altogether, returning the cosmos to matter's old question of coasting or turning back. There are even scenarios, speculative but published, where a fading, reversing dark energy hands the ending back to gravity, and the big crunch, decently buried for a quarter century, walks again. I tell you this, not to unsettle the hour, but to complete the story honestly. As of tonight, the fate of the universe, which the textbooks of 20 years ago described with confidence, is officially uncertain again, pending measurement. The largest question there is has reopened quietly in our own decade, while everyone was watching other news. Somewhere tonight, 5,000 little robots are pivoting in the Arizona dark, 20 minutes at a time, gathering the light that will settle how everything ends. I can think of no lovelier fact to leave beside your pillow. The ending of the universe is, right now, an active area of research, and the universe, so far, is declining to spoil it. Before we close, let's return to the man, because tonight has really been 2 stories braided together, one about the universe and one about a mind, and the second story deserves its ending too. Einstein died in Princeton in April of 1955, 76 years old, working to the end. The notes on the table by his hospital bed were equations, another push at the unified theory that never came. He died believing lambda was the regrettable footnote of his career, the patch he should never have applied. He missed the resurrection by 43 years. And I find myself wondering some nights what he would have made of the news delivered, say, as a headline from 1998. Expansion of universe found accelerating, Einstein term revived. Knowing his humor, which was real and dry, he might have laughed hardest of anyone. Knowing his standards, he might have grumbled that being right by accident is not being right at all. Both responses would fit the man. Neither would change the record. Consider the full arc of what happened to his term, because there is nothing else quite like it in the history of ideas. A great physicist invents a quantity for a reason that turns out to be false, to prop up a universe that does not exist. When the truth arrives, he deletes the quantity in embarrassment and calls the whole episode a blunder. He dies believing it. 4 decades later, the deleted quantity turns out to describe the dominant component of reality, the engine of the universe's future, the pivot of its fate, and it enters the 21st century wearing his handwriting. And now, in our own decade, it may be transforming again from constant to living field, from answer back into question. At every single stage, notice, the mathematics knew more than the man. General relativity permitted the term before Einstein wanted it. The term described dark energy before anyone imagined dark energy. And the equations stand ready tonight to accommodate whatever DSI and its successors find in the same patient way. Einstein built better than he knew, and that is not a criticism. It may be the highest compliment a theory can be paid. He wrote laws honest enough to outvote him. He constructed, in general relativity, a thing more truthful than his own beliefs, sturdy enough to survive his mistakes, deep enough to contain answers to questions he never thought to ask. Most of us, in whatever we build, should be so lucky. There is a lesson folded in here about error itself, and at this hour I'll offer it softly, because it is the kind of lesson that sounds like a greeting card until you watch it operate at the scale of the cosmos. Einstein's blunder was not the writing of lambda. Everyone now agrees the term belongs in the equations. Nature has voted. His blunder, the real one, was the flinch, trusting the consensus of the moment over the strangeness of his own discovery, trimming the theory to fit the fashionable sky. And yet even that flinch, honestly committed and honestly retracted, added something permanent to human knowledge, because the term he wrote in weakness was preserved in the literature, waiting until the universe was ready to explain what it was for. In science, done honestly, even the mistakes are contributions. They are wrong in ways that teach. They leave usable parts behind, and sometimes, once a century, one of them turns out to be a message delivered early to an address that did not exist yet. The discarded page of 1917 was a letter to 1998. Its author misunderstood his own words. The words were true anyway. There is something in that to carry past this one story. The possibility that some of what we each get wrong, sincerely wrong, carefully wrong, is simply right about a world that has not arrived yet. And spare a final thought for the ones who never saw any of it land. Slipher, whose fleeing spirals started everything and who lived to see his measurements absorbed into other men's fame. Friedman, dead, At 37, the first human being to hold the expanding universe in his mind, told by Einstein it was suspicious. Lemaitre, scolded for abominable physics, who lived just long enough to hear on what was nearly his deathbed that the Big Bang's afterglow had been detected and his abominable universe was real. Gamow, who carried the blunder story to the world, the supernova hunters working their mountain-top nights, expecting to time the universe's breaking and finding its foot on the accelerator instead. None of them got the whole answer. All of them moved it. That is the same relay we watch every night on this channel. And tonight it ran a full century. Say it once, quickly, the whole arc, the way you'd trace a lifetime on one hand. 1917, a term is written to stop the universe. 1929, the universe declines to stop. 1931, the term is erased in embarrassment. 1998, the dying stars reveal the term was real all along and in charge. 2026, the term itself wavers, and the ending of everything quietly reopens for measurement. One letter, 5 acts, 109 years, and the baton, right now, is in the air again, mid-handoff, to instruments still counting their photons and students still in school. The story is not over. It is barely, in the deepest sense, begun. Now, as we finally come to the end of tonight's journey, let the history and the percentages dissolve and keep only what this story does to the night sky above your roof, because it does do something, and I think it is the opposite of what you might expect. You could hear tonight as a story about insignificance. Our atoms are 5% rounding error, our galaxies driftwood on an invisible tide, our future a long letting go. But lie with it a moment longer and feel where the weight actually falls. The dominant power in the universe, the thing that outweighs every star and every dark halo combined, is so gentle that it cannot disturb a single hair on your head. It cannot ruffle the harbor you sleep in. It works only in the emptiest places over the longest times, with a patience that makes geology look frantic, and its grandest scheduled achievement, the slow dimming of the far sky, will not be noticeable for spans of time that make the age of the Earth a rounding error. We discovered the ruler of the cosmos, and it turned out to be the quietest thing in it. Whatever governs the universe, it is not in a hurry. There is, I think, a strange, deep comfort in that, one your body can take to sleep, even if the mind lets the details go. The strongest force of all, and it has chosen everywhere and forever the gentlest possible touch. Think of the chain of hands one last time. Einstein patching his masterpiece by lamplight and hating the patch. Friedman reading honest equations honestly and dying unthanked. Lemaitre keeping faith with an abominable universe. Hubble and his mountain changing the greatest mind alive with a single diagram. The rival teams of the 90s checking each other into an impossible truth. The robots of Arizona pivoting tonight. every one of them wrong about something, every one of them adding something that outlived the error. That is how the species learns, not by being right, but by being wrong in increasingly magnificent ways, each mistake bigger-hearted and better instrumented than the last, until one of the mistakes turns out to be the answer wearing a disguise. And notice, finally, what this story quietly promises about the future of knowing. Twice in 1 century, the universe turned out to be mostly made of something nobody had imagined the generation before. First, the dark matter, then the dark energy, each discovery demoting everything previously known to a smaller slice of the whole. Some find that discouraging, as if ignorance only compounds. I'd offer you the other reading, the one that belongs to this hour. The universe has depths that keep being worth the trip. Every time we built a finer instrument, reality produced a new majority, a new mystery, bigger than all the solved ones together. There is no reason to believe that has stopped, somewhere in the 95% we cannot name, or in the 5% we can. The next demotion is waiting, the next scribbled term, the next abominable idea that turns out to be a message addressed to a century not yet born. Thank you for joining me tonight across a century of the universe's strangest idea, from a discarded scribble in Berlin to the engine of everything, and to the edge of the newest mystery, which is still being written by starlight onto detectors as you drift. If tonight's journey brought you rest, or gave your thoughts somewhere vast and gentle to wander, a like or a subscribe helps more of these nights get made, and it means more to this small channel than you'd realize. But that's for the morning. Nothing more is asked of you tonight. One more breath before the last picture for the part of you that keeps score. Nothing you learn tonight asks anything of you. The acceleration will not change your Tuesday. The 5% that is atoms includes, after all, everything that has ever mattered to anyone. Every meal, every voice, every hand held, every night's sleep, the entire address book of love, all of it drawn from the minority ingredient. The universe may be mostly mystery, but the part that hugs back is entirely ours. So let it all go now. The lambdas, the percentages, the fates. Keep only this. Out beyond your ceiling, beyond the last street light and the harbored stars, in the great open water between the galaxies, the quietest power in existence is doing tonight what it has done for 5 billion years, making a little more room. More space between the islands, more dark between the lights, more universe, arriving silently everywhere all night long at no one's request and to no one's harm. The universe is not being taken from us. It is being given more of itself, endlessly, and if the newest whispers from the mountaintops are true, even that gift is still capable of changing its mind. You can sleep inside a story like that. You are inside it either way, and you could not fall out of your harbor if you tried. Sleep well tonight. Good night.